All right, good afternoon, everyone. Thanks for joining us today for our weekly Urban Water Innovation Systems webinar. We're excited to continue the Thrust B series with a presentation from Dr. Brian Bledsoe and Tim Stevens at the University of Georgia. So Thrust B focuses on innovative technological solutions using the data, models, and enhanced process understanding developed in Thrust A. These solutions include building to community scale resource recovery and reuse systems, hybrid centralized, decentralized water infrastructure systems, fit for purpose water systems, green infrastructure, sustainable urban drainage networks, and resilient floodplains. The complete Thrust B series schedule is also available on our website. We'll continue to record each webinar and post to our YouTube channel, and as always, a link to the video will be distributed as soon as it's available. A quick reminder that you have all entered muted, so please use the questions or chat queue to ask any questions, and we'll address them at the end of the presentation. Make sure to join us next week for a presentation from Dr. Matt Zakarabi at the One Water Solutions Institute here at Colorado State University as he explores flood risks to assets in a changing world. And also next week, on Friday, September 1st, Dr. Sybil Charvel will be presenting a separate webinar through the CSU Extension Services Office on graywater reuse systems. So that webinar has been added to the UN calendar, which is available on our website. So if you want the meeting details, you can go there. And I'll send out a link next week once we get Brian's video posted as well. All right, and with that, I'm excited to introduce our presenter for today, Dr. Brian Bledsoe. Brian is a professor of civil and environmental engineering in the College of Engineering at the University of Georgia, where he conducts research on hydrology, hydraulics, river engineering, and infrastructure. So we're going to turn the controls over to the East Coast. Bear with us for just a second.
Excellent. Good afternoon, everyone. Greetings from Athens, Georgia. It's good to be with you. Tim Stevens, research associate and PhD student, is here with me.
Hello, everyone.
We're going to be doing a little bit of tag team like Tom Meixner and Yoga did a few weeks ago. And first off, I'd like to acknowledge our collaborators at the University of Maryland, Baltimore campus, Andy Miller and Gina Lee. We appreciate all their help with this presentation. You're going to see some of their late-breaking results, and also I want to acknowledge Tom and Meixner and his group, and Jim Smith and his colleagues at Princeton University. So this is definitely a group effort. So let's get going. So here's a quick outline of what we're going to talk about today. We're going to start out with why we care about this topic and sort of look at the status quo of current techniques for estimating flood hazards. Then we're going to delve into some of the limitations and perhaps shortcomings of those approaches and various sources of uncertainty that we're trying to advance the science a little bit in terms of being able to incorporate those into our flood hazard analysis. And then we'll get into a few specifics of our techniques and current results in our research activities. And then talk, the last two bullets are about integration across projects at Princeton dealing with rainfall and climate, and at University of Arizona dealing with the green infrastructure and hydrologic modeling, rainfall runoff response, and then close out with some connections with social sciences and some of the other broader UN activities. So I don't need to belabor why urban floods are a matter of concern. They are one of the most frequent and costly and dangerous hazards in the world, including the U.S. And I think it's fair to say current methods are hindered by a poor understanding of a dynamic world and how interactions between rainfall and changing land use and changing channels and floodplains all interact with human behavior as well to affect flood hazards and the occurrence of disasters. So we're going to get into some of those interactions today. And another really fundamental motivation for the UN project is to try to look for these win-win situations in cities where we can identify strategies to improve flood resilience that have far-reaching benefits across many sectors and address many aspects of well-being in urban areas. So, for example, can revitalization of stream and floodplain networks provide a whole host of other co-benefits if we are strategic about it. So some of those basic questions related to green infrastructure that are driving this research is basically, what are realistic expectations about the efficacy of green infrastructure to mitigate floods? Certainly building natural sponges in cities is a rational strategy, but we really don't have much understanding about how green infrastructure scales up at a watershed scale and how its efficacy changes across regions, and really what are the limits of this urban sponge in terms of addressing floods in different regional contexts. And as I already mentioned, ultimately we're interested in exploring how green infrastructure can simultaneously address flood hazards and amplify other co-benefits. So let's talk briefly about the status quo. The FEMA National Flood Insurance Program approach is basically to delineate what we might call a deterministic floodplain. It's a floodplain with a bright line in the sand that says, here is the edge of the floodplain and you're either in or you're out. There is some resolution within that floodplain in terms of distinguishing between a flood fringe and a floodway, in terms of what's allowed in terms of human activities in the floodplain, and we won't get into the details of how that's determined, but the bottom line is that you end up with a map that doesn't really represent the uncertainties in the edge of the floodplain. So it doesn't matter if the confidence bands around the edge of the floodplain are 10 meters wide or 1,000 meters wide, you still get the same line. Now that's not to say that engineers don't use expert judgment and conservative assumptions in doing this, but I do think it's fair to say that there's an absence of information or communication about these interacting uncertainties and processes that we're going to explore in a moment. So just as one example here, this is Bronx Wash in Tucson, and this is where Tim has been out in the arid west working with Tom Meixner's group, and you'll see a couple of other slides depicting this floodplain, and in this example this is a deterministic representation of the 100-year flood, and it's pretty much confined to the street in this area that we're looking at. This is the 100-year event, or the event that has a 1% probability of being exceeded in any given year. And we'll contrast this with some other ways of mapping floodplains in a moment. And so in the current approach, there are many decisions and inputs and parameters that have to be defined. We have to define boundary conditions in terms of what's happening on the downstream end of the channel and providing hydraulic control. We have to provide geometry to our hydraulic models, and there's certainly measurement errors and issues with that in many cases. We have to specify parameters in the hydraulic model like flow resistance and energy loss coefficients, and then there's the overall one-dimensional model specification, which introduces additional error, and then we impose water surface profiles onto a floodplain terrain model and get flood inundation extents. So I think you can see across the input data, the parameter specification, the model specification, and so on, there's propagating errors that can add up. And so the panels on the right just depict a one-dimensional floodplain analysis in HEC-RAS where a steady 100-year discharge is imposed on the topography to yield a deterministic floodplain boundary, either you're in or you're out. So let's explore some sources of uncertainty in flood inundation mapping. A quick list of things to consider would be uncertainty in what's happening with extreme precipitation. For example, here in the southeast U.S., we're seeing some evidence of shifting seasonality and intensity of rainfall where maybe mean annual precipitation is roughly bouncing around the same mean, but it appears that we are having some more intense, hard-hitting events in some cases, and of course rapid urbanization, especially along the I-85 corridor connecting Atlanta and Charlotte. So a lot of things in flux, changing drainage infrastructure and evolving stormwater controls, channels grading or accumulating sediments or incising, woody debris and in-stream wood can play a role in a lot of places, vegetation encroachment and so on. So there are a lot of considerations here. Just to touch on a few of these, here is a regional flood frequency analysis of gauged sites in the southeastern U.S. And you can see for this relationship at a drainage area of about 10 square miles, there's an order of magnitude of variability in these estimates, and the regional flood regression equations are largely dependent on drainage area as the primary variable. So, so discharge and whatever the design discharge is, whether it's a 100-year discharge or something else, has substantial uncertainty associated with it. And this is true whether you have gauges or you're relying on hydrologic models, because especially in smaller streams, there's the vast majority of them are not gauged. The gauging network is kind of skewed towards higher stream orders, and so this is uncertainty in discharge is one of the more obvious fundamental variables that we're going to explore in our Monte Carlo analysis here in a moment. Here's just an example of Bronx wash again, showing what happens when you introduce ±2 standard deviations in that 100-year design storm, and on the right, Edwards Branch in Charlotte, North Carolina. So it makes a big difference in terms of how much of these streets are inundated in Arizona and these residential areas in North Carolina, in two of our study areas. Here are some photos of channels that are influenced by vegetation that's varying seasonally, and often we see big differences in manning brings in and vegetative influence, especially in channels that are less than about 20 meters wide. And of course, here on White Marsh Run in Maryland, channel aggradation can reduce flood conveyance capacity. So we have interactions between climate, changing land use, and changing channels. In a really nice study done by Louise Slater and others and published in, I think this was JGR, is that right, Tim? Journal of Geophysical Research or Geophysical Research Letters. Anyhow, Louise Slater and others, 2015, looked at the effect of changing flow frequencies versus changes in channel capacity in terms of their effects on flood inundation surfaces, and they found significant trends across much of the U.S. in terms of both these factors having a significant effect on flood inundation surfaces, and in many cases there were both influences present in several locations. So in this context, I did want to mention some recent research we just finished up on the Front Range of Colorado. This is just recently published in Geomorphology, collaborating with a couple of my former students, Steve Yoakum and Joel Schultes, along with Julian Scott at the Forest Service in Fort Collins. And basically, in terms of trying to understand how channel dynamics may play into flood hazards, we used the September 11 through 13, 2013 floods along the Colorado Front Range as a case study to try to look at relationships between hydraulic metrics, specifically stream power, and different styles and degrees of channel change as a result of those floods, which occurred in a lot of different geomorphic settings along the Front Range. And to make a long story short, we looked at over 500 stream segments, over 220 some odd kilometers of channel, and you see a map on the left there, and then on the right there's a couple of contrasting photos. On the top, pre-flood and post-flood, you see in Big Thompson Canyon along Highway 34, there's what we call the Category 5 channel adjustment, where there's a full-on avulsion of the channel, and it takes out US 34. In the lower panels, there's significant widening and aggradation in the channel, but it's staying predominantly in its original course without a major avulsion, so that would have been a Category 4 response. And so again, to kind of cut to the chase here, we did have some success in distinguishing among these different categorical levels of channel change using unit stream power or stream power per unit bed area in watts per meter squared. That's essentially just the specific weight of water times the discharge times the slope divided by the width of the channel. And the upshot was this figure on the right, where we sort of aggregate all of the data and relate the risk of or the probability of these different degrees of channel adjustment to varying levels of specific stream power. And ultimately, we would like to do this for some of the other regions and try to account for uncertainties associated with, both channel aggregation based on regional observations like Slater, and also using a stream power approach to get at channel changes besides just aggregation, gradual aggregation over time. Okay, so let's talk about how we might do this better. And I think at this point I might turn it over to Tim and let him say a few words, especially since he's been doing all the heavy lifting on running Monte Carlo, hundreds or thousands of realizations of HEC-RAS runs, and I think for the first time to our knowledge, he's got roughness and discharge and channel topography all changing at the same time. So I'll let him introduce you to some of that work real quick.
So as Dr. Bledsoe previously mentioned, there's the uncertainties associated with the model itself, and then additionally with changing climates and land use. And so how we will incorporate these into this project is a top-down approach as we collaborate with Jim Smith's group and Tom Meichner's group, as Jim Smith models the rain distribution through the stochastic storm transposition that he covered last week in his webinar. We can take the results of that that have a built-in sort of statistical distribution around the uncertainty in rainfall rates and apply that on the hydraulic models that Tom's group is putting together, and then we can run those results to feed input discharges into a Monte Carlo simulation where we run hydraulic models that account for that uncertainty and discharge, but then we vary these additional parameters such as floodplain roughness and topography. And the output from that is a statistical distribution of water surface elevations that we can then turn to a probabilistic floodplain map. And here is a better depiction of that, where we take these statistical distributions around the parameters and randomly sample those, and then run a simulation of HEC-RAS, and we get an output of a water surface elevation, and then we do this a large amount of times, whether it be 500, 1,000, or 100,000, and we get our distribution of water surface elevations. And we get a probabilistic floodplain map, and we can account for these uncertainties by looking at the variation around your probability to inundation rather than being simply in or out of the floodplain. And additionally, we can start to look at these things in more socially relevant timescales. As we look at, there's a 1% probability in any given year of being inundated by the 100-year flood. However, there's a 26% probability of being inundated by the 100-year flood over the next 30 years. And so when you look at this over a planning horizon and look at that risk, you can start to see it becomes a lot more clear that you're much more likely of being inundated. And so we can start to communicate these in better methods as we look at probabilistic maps that communicate probability or reliability over these socially relevant timescales.
Yeah, thank you, Tim. And just on that last slide, in case you're wondering what reliability is, that would be one minus the risk of the flood event happening in the time frame that Tim was talking about, sort of a design horizon or planning horizon. So in this case, the map you're looking at is conveying to the viewer the probability that the flood won't happen in the next 30 years. And this notion will come up again at the end of the talk, where we hypothesize that if we communicate these flood risks to various stakeholders, whether it's the politician or the layperson, that if we communicate them in terms of a risk or reliability in a time frame that they can relate to, like a 30-year mortgage, then we're going to improve the effectiveness of communication. I'm going to run through a few quick slides here that highlight some of the work that Andy and Gina have been doing at the University of Maryland, Baltimore campus. As Jim discussed in his presentation, some of those watersheds around Baltimore maybe are not the absolute flashiest in the country, but they are among the flashiest, and just unbelievable unit discharge rates coming out from these watersheds. Not much infiltration at all to speak of. So what you're going to see are some 2D HEC-RAS models that Andy and Gina have been working on for these less than 15 square kilometer watersheds with really high imperviousness and not many stormwater controls. These are short, hard-hitting rainfall events, so they're doing unsteady modeling, unsteady flow, and part of the goal here is on our end, we're working a lot on the Monte Carlo analysis with the 1D HEC-RAS, and they're really fine-tuning the methods for the 2D approach, and also exploring channel change in the Baltimore area, because a lot of these streams in these hyper flashy watersheds have either blown out and been converted to maybe what is their ultimate successional state of being a concrete trapezoid, or other ones have been restored, and people have at least tried to glue them back together, but many of them have had multiple blowouts, and so these are some dynamic channels. And just quick snapshot of the methods. They have repeat LiDAR. They're also utilizing structure from motion with UAV flights. They're spatially varying the Manning's N values. Again, this is HEC-RAS 2D unsteady for a range of return periods, and exploring changing channel geometry. And ultimately the outputs are not just water surface profiles and inundation extent, but 2D velocity fields and flood wave attenuation. This UAV data, these data give you a sense of the spatial heterogeneity and geometry and Manning's N, and give you a feel for the resolution of the input topography. And here are just a few quick animations of the 2D HEC-RAS results, and we have these for a variety of return periods and channel geometries, before and after incision, and so on. One classic example is, again, White Marsh Run in Maryland. This restoration site blew out and there was lots of aggradation. So this kind of gets at the trade-offs between doing upland GI green infrastructure in the watershed and trying to build those sponges across the city versus trying to restore stream corridors and reconnect floodplains and introducing uncertainty there in terms of, I'm of course a big fan of stream restoration, and I'm not advocating concrete channels, so don't take it that way, but there are limits to what we can do with stream restoration in urban areas. So ultimately what we want to do is combine the two approaches where we're not sure it's practical to do thousands of realizations in HEC-RAS with the 2D model, and we're dealing with some issues with how do we handle bridges and hydraulic structures in the 2D model when all of those capabilities are not quite there yet in HEC-RAS. But what we can do is we can identify some really important scenarios that we're interested in the 1D analysis, and then translate those over into the 2D world and simulate them and generate scenarios that represent different quantiles on the probability spectrum, for example. So let's talk a little bit. I think if you saw Jim Smith's presentation and Tom Meixner's, you have a pretty good idea of how all this comes together, but we're sort of at the bottom of the hill in terms of at the top there you see the stochastic storm transposition idea that Jim talked about, and that essentially gives us a spatially registered intensity, duration, frequency curve, and also a storm catalog that we can experiment with and start to account for the influence of urbanization on storm structure and intensity. And then in the middle, it's not just urbanization and land use change, but it's also the spatial distribution of different green infrastructure practices. And so this is what Tom and Yoga and Tim talked about a couple weeks ago, where we can use Kinneros to distribute different green infrastructure and perhaps hybrid green and gray stormwater practices across watersheds and explore differences among regions in that hydrologic response, and then ultimately feed that into our floodplain models at the bottom of the picture, and that's what our focus is today. So again, just to reiterate, we're trying to crack into this difficult problem of non-stationarity in climate, land use, and river channels at the same time with exploring stormwater practices and how all of those interactions work across our study regions. So I'm going to turn it back over to Tim here for a minute, and he's, I think it was really a fantastic experience for him to be out in Tucson working with Tom's group this summer, and he's going to tell you about he touched on this in the webinar a couple of weeks ago, but he's going to speak to this event in Bronx Wash that he captured, and this sort of represents the a first step in linking our Kinneros 2 hydrologic modeling with our probabilistic floodplain mapping.
So the graph you're looking at on the screen right now is a hydrograph that was output from one of Yoga's Kinneros 2 models of a storm on July 19th. And we took the peak flow from that hydrograph, 238 CFS, and we were able to route it through a HEC-RAS model. So the HEC-RAS model, you can see the inundation extents estimated by that on the figure on the left, and then the figure on the right, we were able to actually go out on that day and snap a picture of the flood. The picture is probably a little on the falling limb, so just after the peak, but you can see by visual inspection that we estimate those flood extents fairly well. So that's, you know, some of the current work where we're bringing these components together, and I think Yoga's working with Jim to get some of the stochastic storm transposition and radar rainfall fields to bring those into the hydrologic model, and then we'll be able to further feed those into the HEC-RAS models and bring this into a Monte Carlo framework and develop a probabilistic floodplain map for this particular location. And so that should be coming soon.
Thanks, Tim. So just starting to wrap up here and look at broader connections among the different UN research activities, we feel like these probabilistic floodplain maps have the potential to be sort of a platform or perhaps a template or a backbone for exploring all sorts of opportunities with respect to green infrastructure in cities. For example, we've got this question of, you know, how do we balance upland green infrastructure with working down in the floodplain and reconnecting floodplains and so forth, and ultimately, how do we try to start maximizing benefits for people in terms of moderating urban heat island effects and improving well-being, and also providing ecosystem services and benefits for improved water quality and biodiversity. So we're looking forward to putting our heads together with a lot of our collaborators like Daryl Jenneret and others that are exploring you know, the vegetation processes in the city, and I think it's going to be really fascinating when this all starts to come together. And we have a meeting here in Athens in a few weeks where we're really going to try to hammer out our vision for some of those connections and our goals for bridging with our friends in, you know, more of the ecological and social side of the project. So I did want to mention a connection with Sharon Harlan's work and Elizabeth Mack's work. We're engaged in developing a large survey and doing some geographic information system analysis with floodplains and census data and so on to try to understand some of the environmental justice issues and some of the perceptions out there across regions in terms of how people think about floods and perceive risk. There's a large body of literature sort of asking the question, do people understand, you know, do people walking around on the street, the layperson, understand the 100-year flood? And I think the answer is a resounding no, they don't. But we still seem to be stuck with that as the standard currency for communicating flood risks. And so, you know, just to reiterate, one of our hopes in this project is that these maps don't just become an academic exercise or you know, another nice picture in a scientific journal, but they're actually something that we can translate into practice working with local governments and decision makers. And here are a few cartoons that we included in this survey that I mentioned, where we asked people questions about not just their understanding of the 100-year flood, and for example, you know, which one sounds the worst to you, the flood that has a you know, it's a 100-year flood, or a 1% chance in any year flood, or is it the flood that has a 26% chance in the next 30 years? So these are some of the cartoons that are incorporated into this survey to try to understand which way of conveying the information people find the most useful in their lives. So this is the conventional, you know, FEMA approach of the floodway and the flood fringe, or how about likelihood of flooding in any given year. Sitting over there at that 1% line probably doesn't sound too scary, but now what if I say, what's the likelihood of flooding in your 30-year mortgage? Oh, it's over 1 in 4. That sounds very different, even though it's the same risk. It's just communicated differently. So it's nice to have, you know, not only have this range of climates and these great groups working in different parts of the country and hydroclimatic regions and biomes, but our sites also encompass a range of different vintages of development and urbanization, and some pretty dramatically varying socioeconomic conditions. So we're really excited about working with Sharon and Liz and others on the project to explore how, you know, the relationships between flood risk and the locations of disinvested or disadvantaged communities vary across regions, and intersect that with, you know, differences in the physical setting to try to understand flood hazards and how to communicate them more effectively. And we'll just conclude today by saying that we very much appreciate the opportunity to have this conversation with you today, and we welcome conversations about collaborations going forward, where we try to achieve some true integration of the physical science and the social and ecological coupling with those physical systems. So with that, I will conclude, and here's contact info for the flood hydraulic modeling team, and at this point we'd be happy to entertain any questions.
Well, I don't see anything coming in, but you see there's contact information for everybody right there. So feel free to shoot anybody on the team an email. I'll get the video posted in the coming days and send the link out to everyone. We look forward to seeing you guys next week. Have a wonderful afternoon, everybody.
Thank you.
Thank you.
Take care.
Bye-bye.